Hello everyone. Hopefully you can see me behind the camera, so I'm here. My name is Sergey Suslov. I'm a professor of applied mathematics at Swinburne University of Technology in Australia, in Melbourne. And I came here to deliver a subject which is based on my long-term research in hydrodynamic stability. So I have been asked questions whether this is only about fluid flows. And as you will see from the discussion which will follow, no, it's the ideas of stability are quite general ideas. And they are found in pretty much every field of engineering, science, and in every moment of your own life, you can see the phenomena which could be related to instability. So I'll just give you a few examples. Just taking common objects like, for example, these ones. You might not be able to see that. Can anyone guess what that is? From the distance you are obviously might not be able to see that, but I just come closer, sorry for the camera. So what do you think that is? So I'll pass it on, just give it back to me please. So what you see here is a common object which is just the core of a ball pen, empty, and just chop the ball off the tip of it. So pretty much this is a piece of rubbish. But look what I can do with it. So if I just hold it like that, it is pretty much straight. And then I start squeezing it. And nothing happens. And we don't expect anything to happen, but if I squeeze too strongly, it buckles. So this is, believe it or not, this is the effect of instability. And this has nothing to do with fluids and more probably to do with the mechanical strength of the material. Okay, I'll show you another example. And this is, what do you think that could be? It's just a pendulum which I made out of well, some cord and some piece, I don't know what that is, it's probably a key holder or something like that, which I just found in my drawer and attached it to this. And if you look at this, this is an example of another system, physical system, which can undergo instability. Watch. So what do you expect will happen if I just start spinning it? Not much, right? It spins because I pinched it here and it spins. And we expect that this will continue independently of how quickly I spin it. Right? But now let me just see if I can demonstrate it. If I do it this way. Did you see what happened? It actually developed like a bulging. Right? So it didn't stay straight. It started moving like that. And if you play with it, I will pass it around. And if you do it very quickly, you will see that the shape of this cord is not necessarily just like that, like parabolic. It might be like that, depending on the speed. This is again an example of instability. Okay? I'll pass it around, all these toys around later on. What do you think this is? Have you ever seen this toy before? So what you see here is a toy which some call Landau spinner. So, and again, I will pass it around, but similar elements. So if I spin it on the floor, you expect it to spin like that in upright position, because if it is not spinning, it just stands like that. But watch what happens. It actually turned upside down and spins like that. Again, this is a result of instability. So I'll pass all these objects around so you can play with them. So just please return them to me once you finished with them. But the point is, the instability is not limited to any specific area of engineering or area of life, right? It's everywhere. We see it all the time, but we might not pay attention to that and even don't recognize that we're dealing with instabilities, but that's what that is. We expect one thing, but it didn't happen. Something else happened instead. So, and transition from one state to another is that what we are going to investigate. So we will see how we can treat this type of phenomena mathematical. So to do that, I will start with a very simple algebraic model. So the model looks like that. So this is ordinary differential equation that many of you have seen before, so just generally differential equations, right? So, and A is the abbreviation for amplitude. We will see that the context in which this equation will appear is amplitude of so-called perturbations later on. But for the time being, I would like to focus on this equation on its own, right? Algebraic equation. And before I go, I'll just ask you some questions about your background, because I obviously have never met you before. I don't know what subjects you've studied before. Could you please tell me whether, just honest answer, whether you had any formal subjects on differential equations, ordinary differential equations? And if you have not had them, no shame, just raise your hand. I need to calibrate the audience. Okay, some people do not know what differential equations are. I haven't seen before. You know, but not formal subject. Okay, right. Another thing I would like to check, vector calculus. Is there anyone who hasn't been exposed to vector calculus? Okay, so I just need this to make sure that I explain the relevant concepts when we come to that. And partial differential equations. Right? And introduction to any sort of fluid courses, Navier-Stokes equations, something like that. So there are people in the class who haven't seen that before either, right? Okay, good. That's nothing to be afraid of. I will go through all this, but what I will do, I will probably go a little bit quicker through that, because majority of people in the classroom already had some idea about that. But I have detailed lecture notes, which I will be able to distribute after the lecture, and you will be able to pick it up from there. So, all right, go back to this equation. So what can we see about this equation? So left-hand side is derivative. It is a rate of change. So if function changes, then the left-hand side is not equal to 0, but it is equal to the right-hand side. And the right-hand side must match the left-hand side, of course. It's a trivial fact. But if the left-hand side is 0, then the right-hand side must be 0 as well. Okay? So, if the left-hand side is 0, consider dA by dt is like a velocity. Velocity is equal to 0. Nothing moves, right? Which means the position is fixed, and this is called fixed point. Okay? So, how do we get the fixed point? We look at this equation, we identify derivative, time derivative in this case, we'll treat it as a time. We set it to 0, and we solve the resulting algebraic equation. So therefore, from here we will simply get sigma plus k multiplied by a squared multiplied by a is equal to 0. So this is factorized form of the equation of the right-hand side. How do we make it to 0? Well, clearly we either say that a is equal to 0, or sigma plus k a squared is equal to 0. So from here, well, clearly that a is equal to 0 is the direct solution. From here, we will get that a is equal to plus or minus minus sigma divided by k, square root of that. Now, of course, this equation has solution for any values of sigma and k, except if we are interested specifically in physically relevant solution, which is a real solution, then we have to make sure that the expression under the square root is positive, which means sigma and k have to have different signs. If sigma is positive, k has to be negative. If sigma is negative, then k should be positive. Is that clear, right? All right. Next thing, let us draw the so-called phase diagram. So, what is the phase diagram? Or rather, maybe not, I will not call it phase diagram, I will call it the equilibrium diagram. And I will choose sigma to be so-called bifurcation parameter. So we will see what I mean by that. So sigma is just this constant. This is the value which we will try to change from minus infinity to plus infinity. We will consider all the quantities to be real, and we will see what actually happens. So this is 0. And we have another parameter which is k, and I will simply consider the situation when k is less than 0. Okay? K could be positive as well, k could be positive, but I will leave this case for you to think about on your own. So I'll consider in detail the case when we have negative k. All right. If k is negative and sigma is negative, what happens here? So negative, negative, negatives. Overall negative square root of negative is complex number, right? So therefore, we are not interested in that. What about this part? If sigma is negative, then a equals 0 still makes the right-hand side of this equation 0. Right? So therefore, I can say that a equals 0 is still a solution. So it is a solution, and the graph of that solution is just this straight line. Okay? Now, what happens if k is negative, but sigma becomes positive? So k is negative, sigma is positive, minus in front of it, the whole thing is positive. Square root of that is a real number. Okay? But we have plus or minus. So we will get one point somewhere here, another point somewhere here. And what if sigma is equal to 0? If sigma is equal to 0, clearly this is square root of 0, which is still 0. So we have a branching behavior. These are just square root curves. Okay? So what actually happens here is a single fixed point line, this one, branches into how many? Don't forget that a equals 0 is still a solution, right? If a is equal to 0, so sigma doesn't really matter, right? Positive, negative is still there. So we still have this, but we have two more. So overall, this looks like a pitchfork. And this situation is known as a pitchfork bifurcation. Okay? Very simple. But this, now we are coming back to this equation because it is a differential equation, and it is first order differential equation. So therefore, how many extra conditions do we need to specify to make sure that we get a solution, unique solution? So equation, first order differential equation requires how many conditions? One, right? The number of derivatives is equal to the number of equations we need to specify one condition, and that is called the initial condition. And of course, initial condition is just a number which could be anything. All right. Let me just state that my initial condition is here. So some value. So by the way, that is the value of a. So what happens in that case? So if sigma is negative and a is somewhere here, let's substitute it there in the right-hand side. In the right-hand side, we'll get negative sigma multiplied by positive a. So this term is negative. We decided that k, we chose k to be negative as well, and a is chosen to be positive. So therefore, a cubed is positive. So this is negative, negative, negative. So therefore, dA by dt is negative. What does it mean in terms of the amplitude itself? So which way will it go? So rate of change is negative. So therefore, the quantity will decrease. So, and it will decrease, and it will decrease all the way to 0. Right? Well, what if I choose the point here? If I choose the point here, so this is negative, overall this is positive. This is negative, overall this is positive. So therefore, the rate of change would go positive, so it will go up. Where will it go? It will go there. Okay? But let us look at what happens here. If I'm at this, somewhere at this point. So let's look at this. So sigma A. Sigma is negative, positive now. A is positive, so therefore this term is positive. K is negative, A is positive, so therefore this term is negative. Positive, negative. Which one is going to win? Remember, this is A, and this is A cubed. And look what I did. I chose A to be close to 0. It is small bit, right? If it is small, then which term is larger? A or A cubed? A. So therefore, this is going to win. If it wins, then overall derivative will be positive. It will start growing. And it will go that way. And it will hit this parabola eventually. But what happens at this parabola? At this parabola, there is a balance between the two. And once you reach this point, your velocity, your speed becomes 0. You cannot move any further. So therefore, you will stop here. And if I do the same thing here, I will show that exactly the same happens, but in opposite direction. So which means that no matter where I start here, I will end up at 0 if sigma is negative. But if I start here, close to the positive part of sigma y, I will end up on a parabola rather than at 0. Unless I start at 0 exactly. If I start at 0 exactly, what happens? You will stay at 0. Okay, so this is still a solution. This is still a fixed point. But any initial deviation, no matter how small, will push you away from it. So the situation here is called stable fixed point, stable equilibrium. Situation described here is called unstable. So therefore, what we'll see that one stable equilibrium branches into two stable equilibrium and one unstable one. Okay? Just to finish it off, I'll pick a point here and see what happens. So here, A is positive, sigma is positive. So this term is positive. K is negative, A is positive, so therefore this is negative. But here, A is large. So therefore this term will win. And it will push everything, the dynamics down. So therefore we will end up at this problem. So this, therefore, this is a stable equilibrium. This is stable equilibrium. This is unstable equilibrium. And this is a stable equilibrium again. So the situation in which one equilibrium, stable equilibrium, bifurcates into two stable equilibria and one unstable and produces one unstable equilibrium is called supercritical pitchfork bifurcation. So, and that is, believe it or not, that is the essence of stability analysis that we will be going through, with a lot of details, physical details being added, but that is exactly what we will observe in various physical systems. And the origin of those physical systems could be fluids. That's what all examples in these subjects will come from, where they will come from. And all other physical areas will experience the same type of behavior. It is completely generic. So therefore, if you are not particularly interested in fluid applications, you will still be able to benefit from the general ideas which I will introduce here. Okay. So that is something which we'll keep investigating. All right. What I did here is quite intuitive, qualitative analysis. So there is a little bit more rigor that we can add to this discussion. So even though what I've done here is fully sufficient to understand what is happening, let me do a few things algebraically. Specifically, what I will do, I will introduce so-called linearization procedure. So what is linearization procedure? Linearization procedure is essentially considering dynamics which is close to some fixed point, and so close that any nonlinear function over deviation from that fixed point can be neglected. So if a is small, then a squared is even smaller, and therefore we neglect a squared. If a is small, a cubed is even smaller, and we neglect a cubed. Okay, so that's basically what we will try to do. Now, so let me call, just to introduce a reasonable notation, let me call this combination square root just small a. Actually, maybe not, let me a second thought. What I will do, I will call this a bar. So, and then I will write a is equal to a bar plus a, where a is a lot less than a bar. So what do I mean by that? So this is my a bar, so this quantity here is a bar. This is the location of a fixed point. So what a bar does, if you substitute a bar into this equation, then you will get 0 is equal to 0. Okay? Because by definition, a bar is obtained by setting the right-hand side to 0. And a is that small deviation. So if I consider 2 points which are close, one of them is on this parabola, that one is just off that parabola. So this will be this distance here, this distance here is my a. Okay? So what happens in this case? Let me just substitute this in. I will get dA by dt plus dA by dt. Right? So if a is equal to a plus a bar plus a, substitute on the left hand side, you will get this. Okay? Which is equal to sigma a bar plus a plus k multiplied by a bar plus a. And this is cubed. Agree? So let me expand the right hand side. It will be sigma a bar plus sigma small a plus k a bar cubed plus k multiplied by a bar squared multiplied by a. What's the coefficient in front of it? Tricky question, isn't it? 3, right? So it's from primary school. Not that way. Not that way. Maybe wrong one. Okay, and this is plus. So 3 here plus. What is going to be the next term? It will be plus 3k multiplied by a bar, but a now is squared, right? Finally, plus k a cubed, right? But remember, a is small, so therefore, what I can do, I can go through these terms and neglect everything which is small compared to other terms. So therefore, the smallest one out of all of these will be which one? This one. So I'll neglect this. A squared is the second smallest. Get rid of that. So a bar cubed, A bar. So now let me look. So basically, if I get rid of small a, well, I will lose everything. So I don't want to do that. So I would like to keep one term in small a. So all right. Now let us look at this, and this. What can you say about that? So this is equal to this plus this plus the rest of it. What can you say about sigma a bar plus k a bar? Remember, that's what we have. The condition that essentially the sum of these two terms is equal to 0, and a bar is a constant. We chose it as a fixed point, so therefore its derivative is equal to 0. So therefore all these disappear. This is gone, and this is gone. So eventually what's left is dA by dt is equal to sigma a plus 3k a bar squared minus, multiplied by a. Okay? But a bar, we know what that is. So therefore it will be sigma a minus, or rather plus 3k multiplied by a bar squared, which will give me a minus sigma divided by k multiplied by a, which is equal to, clearly k and k cancels, sigma a minus 3 sigma a minus 2 sigma a. Agree? All right, good. So therefore, this equation, what's the solution of this equation? Do you know that? Can you recognize the solution of this equation without actually solving it? It's exponential solution. When the rate of change is proportional to the function itself, it is exponential function. The only function known to humankind that upon differentiation remains itself is exponential function. So therefore this is the function and that's differentiated function. They are equal to each other, so therefore we conclude that differentiating function does not change the function. Okay, so that's exponential solution, so therefore the solution is a is equal to a0 e to the power minus 2 sigma t. A0 some initial condition, small initial condition. Good. So how does that behave? Remember, we chose this to be positive, sigma to be positive. So we have e to the power minus 2 sigma. Sigma is positive. How does it behave? It goes to 0. Unstoppably. It will die. No matter what, this will drive it to 0. So therefore, anything, we call this quantity here as a perturbation, fixed point and perturbation. So perturbation dies out. We showed it algebraically because of that. So even if you start off the parabola, eventually you will collapse onto the parabola and it will happen exponentially quickly. Okay? So that is algebraic confirmation of the fact that we already learned graphically. All right. Now, let me see where we go from here. So from here, I would like to move on to the concept of fluid equations. Right? So I would like to start applying these very basic ideas to particular examples of fluid flows. And I know that not every one of you dealt with fluid equations before, so therefore I will introduce very, very non-rigorous, I will give you a very non-rigorous introduction to fluid equations. So how does that work? So fluids flow, which means fluids move. Fluids are physical objects, but they are special physical objects because they don't have what? So compared to solids, what don't fluids have? Keyword here is shape, right? If you don't have shape, then it is hard to determine the volume, right? A river flows, we know it is there, we know it exists, it does not have, it is being shaped. What is being shaped? By the surroundings, right? So therefore, if we are talking about any solid object, we have it in front of us, we can see it, we can measure its volume, and that volume will remain fixed in that sense that, well, under normal conditions, the object, solid object moves, but its shape, its volume remain the same. That doesn't happen with fluids. So that's the first difference between solids and fluids. So when solids move, what is the basic principle, mechanics principle that describes their motion? What law?
Law of elasticity.
No, you're digging too deeply. So what is the law describing the motion, the dynamics of solids, so when they move, so motion, not deformation. Elasticity is to do with deformation, just moving as a whole thing, without deformation.
It will move to a fixed amount of...
Newton's law. So how many Newton's laws do you have? Do you know? In mechanics, 3, but there are more, right? There is optics, there is also Newton's cooling law, and so on and so forth. So, but I'm talking about 3 Newton's law as relevant to mechanics. And what are they?
Law of inertia.
Law of inertia, which tells us what? Right, you are very formal. It tells us that nature is lazy, right? Unless you push it, it is not going to respond, right? It's not, nothing is going to change or move. Okay, what about the third one?
Action and reaction.
Again, you're being very formal. So it's a wall, law of the wall. You come to the wall and you hit it as hard as you can with your head. You will feel it, it will hit you back, right? So it's action-reaction. So not those two. Second Newton's law, what does that tell us? So it tells us that the motion is initiated by the action of the force. And the force is proportional to acceleration, or rather forces creates acceleration. And the coefficient of proportionality is mass, right? Again, it is very easy to introduce mass for a solid, right? You just put it on a scale and that's it. Not so easy for fluids because, well, what is the mass of a river? No, you don't know, right? Or ocean. So, therefore, the first thing which we need to get used to when we're talking with fluids is that fluid is still a mechanical object, but it does not have shape. And because of that, we have problems with defining its volume and its mass. So what we will do instead, we will introduce so-called mass per volume, density. Okay? So therefore, in fluids, we will not use mass or volume, we will use mass per volume, which is density. Density is a fluid property, so density of water is taken, for example, fresh water is 1,000 kilograms per cubic meter. So that's what that is. Okay. Another thing is acceleration. So with the acceleration of a solid body, everything is more or less clear. So what is acceleration? So how do you define acceleration? It's a rate of change of velocity, right? Velocity of an object. And if the object is here, the velocity of the object is also here. It's not there, right? And this is the next problem we deal with fluids. Because fluids do not have particular shape, so therefore when we are talking to fluid, we don't know, well, that's the river. What are we looking at? This point, this point, this point, which one? So Gang River is what, 3,000 kilometers long or more, right? So which one? So we introduce a material point. We just say, well, all right, this is a point within the bulk of fluid. It is surrounded by a unit volume. And the mass of that unit volume is equal to, obviously, the density of the fluid, which is measurable quantity. Okay? So the problem here is, then when this selected material point or fluid particle flows, it is surrounded by all other particles. And all other particles also move, and they create the velocity field around this particle. So therefore, particles, they influence each other. It's not like when we are talking about solid object, where you just pick a point, any point on the solid object, and you trace it, and you know that this whole shape will follow it. No, it's not like that in fluids. In fluids, each particle has its own mind, and one particle can go that way, the other particle might go that way. Right? So what we will need to do is to be able to somehow trace what we call velocity in fluids. And the velocity in fluids is introduced as essentially a property which does not describe a particular particle, fluid particle, molecule or anything, but rather position inside the bulk of fluid. So velocity is attributed to a position within the fluid, not to the actual physical fluid element. So that's another thing which we need to be aware of. So now, the concept of acceleration is still the same. It is rate of change of velocity, but velocity now is a more complex concept. So imagine that you're riding hot air balloon. Right, so you are in the middle of the air and you're being carried away by the wind. And what you're looking at around you, so for example, you are trying to sense the temperature around you. So if your hot air balloon is just anchored on the ground, and you're sitting there, you're not moving anywhere, right? So the sun rises, temperature rises, and by sitting in this hot air balloon, you feel that the temperature rises, so even though you're not moving. So therefore, if you consider rate of change of temperature, you will see dt by dt, T capital temperature, T small is time, and you will feel that. You will detect that. Now somebody comes and chops the rope, the anchor, and you start floating. And you go from one area, physical area, to another, and what you will see that the temperature again starts changing, but not because sun just rose, it's just because you're moving from shady place to sunlit shady place, so different geographical location. And this is also perceived as a change. So exactly the same happens with velocity. So velocity has two variations in that. So characterized by two variations. One is variation at a particular location. You're sitting in a particular location and something happens, and as time progresses it changes. And the second time, if you're talking about fluid flowing, you go with the flow, you move from one position to another, and just because of that change of the position, you also feel the change. Both of them need to be taken into account, and this is done by introducing mathematical concept which is called material derivative. Okay? Some of you might have heard that before, so let me just introduce that. So I need to go to the next one, so plus. Yeah. All right. So we are talking about velocity components, say d. Sorry, wrong. Yeah. So du by dt. So I use full derivative notation here. But that consists of two components. One is associated with what happens at that particular point. So you're sitting there, not moving anywhere, and you see that something happens over time. So that's the rate of change. But then you start moving, or fluid moves around you, wind blows and carries you. And this is, therefore, will induce some spatial change. So therefore, you will see variation of the same quantity of velocity associated not with time, but because you're changing position x. But this occurs not instantly. So what is the speed with which you move? Well, that's u speed. So therefore, that's what you have. So this is a variation due to change of position, and this is how quickly it is, just because you move with this speed. Of course, in general, you can move in all sorts of directions. And in Cartesian coordinate, therefore, you generalize that to v du by dy, because v is a component in the y direction, speed in the y direction, plus w du by dz. That's what you have just for a single component. But, of course, we have three-dimensional flow in general. In general, we have all three components. So therefore, we need to introduce dv by dt, which is equal to, and dw by dt, which is equal to. Right? I will leave this as an exercise for you to feel, to see the pattern. So you see that the first term is derivative with respect to time, and then you move in x direction with velocity u, y direction with velocity v, and w in the z direction. So can you tell me what I will need to write here, just to check? So plus
v dv by dy, del v by del y.
Okay, just a check. And then one more. If I'm here.
Del w by del w.
So it will be dw by dt. Okay, I will leave the rest for you as an exercise to fill it in. So anyway, so what we have here is essential expression of the fluid velocity. So therefore, in fluids, we will have Newton's second law written as mass times acceleration, where mass becomes density, and acceleration becomes one of those, actually rather three of those altogether. So we will get dv as a vector by dt, okay? And by vector, I mean it means that we include all three components, u, v, and w, and that will be du by dt, dv by dt as a vector, dw by dt. So three components of derivatives plus u du by dx plus v du by dy plus w du by dz, and I'll just leave this for you as promised as an exercise. So this is just mass times acceleration. So according to Newton's law, mass times acceleration is equal to what?
Force.
Force. So net force, all forces being added together. So let's make one small step at a time. So therefore we will consider first fluids, idealized fluids, which are so-called inviscid fluids. No viscosity there. It doesn't get stuck to anything. So when is it possible? Well, water is pretty much could be considered as inviscid fluid if it does not touch any walls or any surrounding. So in the bulk, far away from the boundaries. Okay? Or air, for example. When we come close to the boundary, no, we cannot do that. But for the sake of just finding a suitable starting point, let's consider this idealization first, inviscid fluid. So viscosity, friction is not there. So if not friction, what other forces do you think can act to move fluid? Just two of them. So there are two main forces. If we neglect viscosity, two main fluid, main forces that act on the fluid. Inertia is, of course, it is part of mass times acceleration. It's left-hand side. We already took care of that.
Particle pressure from this.
Pressure and gravity. So these are the two main forces which we definitely need to take into account. So why pressure? Well, wind blows. Well, how does wind blow? So what creates wind? Pressure difference, right? High pressure, low pressure. Which way will wind blow?
High to low.
From high to low. So, and which mathematical vector calculus concept shows us the direction of change, of quickest change of a quantity? Gradient, right? So if we compute, if we take a function pressure is a scalar function, a function that is defined at different positions and maybe at different times, right? But it produces, if you evaluate pressure, it is a single value, so it is called scalar function. So rate of change, the fastest rate of change of pressure is given by the quantity which is called gradient, mathematical quantity gradient. So upside down triangle or nabla, so Greek letter nabla. That's what the gradient is. However, if we are talking about physical applications of wind blowing, right? So if wind blows, well, it blows in the direction of opposite to the gradient. Gradient shows maximum increase. So if you compute gradient of pressure, you will see in which direction pressure increases. The wind will blow in the opposite direction, right? So therefore, the wind will be pressure in the opposite direction to the direction of the gradient. So therefore, it will be negative gradient of pressure. Okay, so this is pressure, this is gradient, negative of that. And plus gravity. So how does gravity look? It is acceleration of gravity multiplied by the mass, right? But in fluids there is no mass, there is density. Plus rho multiplied by g. Okay? So g is acceleration of gravity. So therefore we arrived in the system of equations, at the system of equations which governs the flow of inviscid fluid, and this is known as Euler equations. Okay, so Euler, pronunciation is funny, it's not like how it is written, so he was, well, ethnically he was German, he lived in and worked in, for Russian, in Königsberg, and then he worked for Russian Academy of Sciences in St. Petersburg, so 17th century. A lot of things attributed to him, in particular that Euler's chart problem. Remember that the core of the ball pen, which I compressed, and the button also was investigated by him, so very productive mathematician. All right, and this equation is written, is named after him. So, what else do we need to know? One important thing about fluids is that they do not have shape, they deform, they flow, and therefore it is very easy to lose fluid. Because it is so fluid. So it is fluid, it flows, and if you do not keep an eye on it, it will disappear. And then you're in trouble because there is a physical law which states that mass is conserved. Conservation of mass. So we have to keep this in mind. So conservation of mass. So, and mathematically this fits in. So we need an extra equation, even algebraically. Can you tell me why I say that? So how many unknowns in these equations? We have u, v, w, 3. We have 1, 2, 3 equations. But well, we can say, assume that this is just given to us, right? So density of the fluid is given to us, gravity is given to us, but pressure is another variable. Four unknown variables here. So U, V, W, and P, and only 3 equations. We cannot solve it. We need an extra equation. And that's where mass conservation principle comes in. So-called continuity equation. So again, I will just write it down for you. And then we will discuss what it actually means. This is called continuity equation. All right. So, dρ by dt is the change of fluid property, of fluid density. So, and some fluids are easy to compress. Some fluids are not easy to compress. For example, imagine a hot air balloon. What, just helium balloon, you know, those toys that you kids. If you take it and you just with your hands and you can squeeze it, right? And if you're careful, even it's small enough initially, so you can actually squeeze it quite strongly, and it will be fully contained in between your palms. Now imagine the same balloon filled with water. Try to do the same. No matter how hard you try, it will bulge. You squeeze it here, bulge in another direction, right? So that's something we to keep in mind. So therefore, this term dρ by dt is change of the density. Like for air, it is easy to do, right? You can imagine that. For water, no, it's probably very hard to do. So well, water does get compressed if you go to the bottom of the ocean. The density of the water there will be higher than the density at the top. But you need to dive there, so well, be my guest. So now, what about these terms? So d by dx, d by dy is essentially change in a particular direction. So what is changing? Product, rho times u. It is mass moving with velocity. And it's not the quantity of mass moving times velocity, it's the variation of that quantity. That's what it means, right? So, literally that means the following. So you have x direction, and you have a quantity rho u, and I will say in, and rho u out. So d by dx of rho u is approximately equal, remember, what the basic, or what the meaning of derivative is, by first principles. It is rise over run. It is increment of a function over increment of the displacement, right? So therefore, it will be rho u out minus rho u in divided by delta x, right? Provided that delta x goes to 0. What do you think the physical meaning of that is? Right, forget about this. That's essentially how much fluid enters this volume here, right? So this is delta x. And this, how much leaves it? Okay? So the only thing is that I made a mistake here. It is the other way around. It's like that. Okay? So the bottom line is that's the difference of how much enters and how much leaves. That's what that is. So therefore, if more fluid enters than leaves, then it has to accumulate. If it accumulates, then there is more mass inside than was a few seconds ago. So that's what will happen. If this is positive, then this is negative, and vice versa, right? Because on the right hand side it is 0. So if the fluid comes in and stays there, the density has to increase. So that's the meaning of the continuity equation. Again, there are formal derivations of these equations. I don't want to spend much time on that because it is quite intuitive, and the best way of approaching this would be from a physical point of view rather than from an algebraic point of view. So this flux in, flux out. Difference stays inside, influences the amount of the total amount of what is left inside, and leads to the variation of density, right? And this happens in all three directions. So you squeeze it this way, but it might bulge that way. Okay? So therefore, thank you, 5 minutes left. Therefore, what we need to realize that this is just a very basic principle of conservation of mass, are written in fancy mathematical terms. Nothing more. But the last 5 minutes I would like to spend on analyzing these equations a little bit more, and by writing it like that. So d rho by dt plus rho, rather not rho, but plus u d rho by dx plus v d rho by dy plus w d rho by dz is equal to, so do you see what I'm doing? So this is a product, I'm just applying product rule. And I kept first term from the product rule in the left hand side, and what I will do, I will push the rest of it into the left hand side, and the left hand side will be minus rho multiplied by du by dx plus dv by dy plus dw by dz. Right? Now, if the fluid is water, density of water cannot really be changed easily. So what is d rho by dt then?
0.
What about d rho by dx?
0.
So all this is 0, but rho itself obviously is not 0. So therefore, we arrive at the conclusion that this thing here, which is known in vector calculus as divergence, just the sum of derivatives, must be equal to 0. Such a fluid is called incompressible. Okay? And we will be dealing, for simplicity, we will be dealing in this subject, we will be dealing with incompressible fluids throughout this module, throughout this study, and that's the equation that we will always use. Last comment before the break. If the fluid is water, but if the fluid is salty water, taken from the ocean, and salinity of ocean is going to change from point to point, density will depend on how much salt is in water, dissolved. So density of ocean water is not constant. Doesn't mean that once the water gets into the ocean, it becomes compressible. We just showed that if the fluid is incompressible, right? Well, if the density is constant, then we have so-called incompressibility condition. And that the condition was derived assuming that rho is constant. Okay. We finished with recording now? All right. So I'll just finish discussing this, and then we'll stop for a break. What do you think?
Change pressure only, then it is only called the incompressible.
So, well, two things. First of all, mathematics does not change physics. That's the basic rule. don't tell me, well, something, well, a physical effect happens because I wrote it in the equation and solved the equation. No, it doesn't work that way. Physics does not care about that. And if the fluid is water, whatever you do with it, it isn't compressible. Even if its density is not zero. So then, what it is important to understand that compressibility condition in many engineering books, it is introduced like fluid with constant density is incompressible. Yes, but not necessarily. Fluid might have non-constant density and still be incompressible. And this seems to be puzzling, but the answer to that puzzle is compressibility has nothing to do with density whatsoever. It is to do with the ability of changing volume. Volume, not mass, volume. And
You can go back to the.
yeah, that's okay. That's okay. I just need to save that.
Yeah, it
before
will be
that. So the volume has nothing to do with the amount of mass. It is this divergence of V which describes what happens to the volume. Divergence V equals 0 means volume is constant. Not density, volume. Okay?